So welcome back to the fun. We'll continue with p-adic six functors in rigid geometry.
All right, yeah. So last time I promised to say a little bit about the QP story. So I guess this will be a bit more informal and shorter. But yes, so as I promised, I will say something about the QP story. So in other words, what are we interested in? So maybe again, let me start with motivation. So again, let X be a smooth, rigid variety over C, which itself is P, and then we can associate the QP cohomology, which is the cohomology in the pro-étale side of X of the sheaf QP, which itself is a pro-étale sheaf. Okay, and okay, we can ask similar questions as before, right? So let's have, for example, Poincaré duality, or more generally, is there a functor formalism for this? Okay, and well, last time I already kind of gave away what I want to do, but before I recall that, let me give 3 examples that maybe indicate like why something slightly complicated has to happen here. Okay, and well, the first example does not really indicate that. It just says that in easy cases, things just merge. So suppose that X is proper. Then in fact, we have our gamma X pro-étale QP is just, well, in this case, well, actually, as soon as X is quasi-compact and quasi-separated, we can compute this as we'll take the limit over n of r gamma X étale of Z not e to the n. And I just invert P. Okay, so I mean this guy here in the middle, this will always be, okay, this is R. This will always be equal to pro-étale cohomology of ZP, just because cohomology commutes with limits. Okay, and there's a subtlety here that étale and pro-étale cohomology, they agree if the coefficients are discrete. So it doesn't matter here if I put étale and pro-étale. Okay, but the fact that I can just invert P outside of the cohomology, that is something that is specific to the fact that X is QCQS. Okay, so in this case, nothing interesting happens. So complete duality reduces to the Z mod P to the n. And this I essentially studied or discussed in previous 2 talks. But there's 2 interesting ways in which one can go from here. The first thing is what happens if X is not proper, and the second question one can ask is even if X is proper, what happens for more general local systems I can put here? And it turns out that both of these questions have surprisingly, well, I don't know, seem to give surprising results, at least if one looks at this for the first time. So let me here recall the computation by Colmez-Gilles-Niziol and Gilles. Maybe for simplicity, let's suppose C is CP. Okay, so this will be the example where X is not proper. So choose X to be the open unit disk. Over CP. Okay, and then Colmez-Gilles-Niziol compute with cohomology, and it gives you. Okay, I'll stop writing the pro-étale here. Keep cohomology, and it sits in degrees 0 and 1. And degree 0 is just QP. Okay, I guess that's not surprising. And in degree 1, it is the functions on X modeled out by CP. And then it's 0 afterwards. Okay, so we see that this guy is huge, like it's a QP vector space. And it also depends on base field, and I guess that's somewhat similar to what I already said happens on P, right? Okay, and well, they suggest a functor where they put the following as the homology with complex support. In this case, it will be well, we'll just sit in 1 degree, and it will be QP direct sum sheaves on the boundary of a good sheaves of X. So this is for ranges 2 and 0. Right. Okay, and like for the sheaves on the boundary, they have some formal definition where you just take coordinates over things that go more and more to the boundary. So now if you look at this, and you're asking if there's some sort of functor-étale for this, well, you see that QP seems to match, right? So there seems to be the usual QP duality. But something weird is happening here. So, well, if you stare at it for a while, what these rings are in this case, I think they're essentially some power series rings. You'll notice that these two rings, they're also dual, but only over CP, not over QP. So the functor-étale that we are hoping for is to somehow incorporate QP duality here and CP duality in these two parts. So something weird happening. And let me give one more example that might be even more surprising. So this one's due to Hansen. Now we just take X to be P1, CP maybe again. But I choose a line bundle, a QP line bundle on that. So, well, last time we had this living tape tower, right? So recall. Okay. Yes.
But I'm confused. You were saying that there is some kind of duality here, but that is strange. So, but sometimes looking superficially in the upper situation for homology without complex support, you have something in degree 0 and 1.
Yes.
And so then we would expect the duals to be degree 1 and 2. But
yes,
the correct answer is that it lives in degree 2.
Yes.
So this is already something.
Yes.
And then you are saying that moreover they are doing some strange. Yes. Okay. So
Yes.
things are the
Yes. So the point of these examples is to explain that things are strange, and then afterwards I'll try to explain how one can make sense of it. I mean, I should also say that, like, for the QP cohomology, these three people have approved of half Poincaré duality and arbitrary sign spaces, so including this unit disk. So they have a definition of this cohomology complete support, and they can show that it will in some select appropriate sense. So they have more or less figured that out. And well, the solution I will present, I guess, is a bit more, well, it's a bit different because I present a six-functor formalism, but the basic ideas are more or less the same. Of how to solve these issues. Okay. So here's something that might be is even weirder. So we have this rigid-analytic space, which projects to P1. Okay, and this guy was parameterizing deformations of a fixed formal group over FP bar. And what I can do now is, well, to each formal group over FP bar, and this map here was a torsor under GL2QP. Right, I'm basically just forgetting the level structure I have on the plate module. I have. And well, I can define a pro-étale P local system called LT maybe, will be taken on P1 by, well, roughly sending G this, I guess, rational tape model. Okay, so this is a local system that becomes trivial up here, where trivial is the tape model.
dimensional.
Yes. Did I forgot to say that? Sorry. Yeah.
So is it just the two-dimensional local system corresponding to this GLP force?
I guess.
Well, naively speaking, this is key.
I mean, it's obviously trivial.
However, I have I'm of course afraid of all this because my understanding is that there is a huge difference between pro-étale and
Yes, it is crucial that this thing is.
it's yes. So for instance, it's not just a moment. Pro-étale QP local system. So it's not. Yes. So my fortunately we had here a talk by Ben Fuller, and he explained to us that in addition, well, there are many more pro-étale local systems than étale ones, and so I don't understand these gadgets. I have to believe that they're very important. Okay. It should. So, so this was in these talks of the p-adic approach theory, and this is related to the future talks on the p-adic Simpson correspondence. So something important, something mysterious for me, and I have to believe.
The Simpson correspondence seems, well, yeah, one way to say this, I guess, it seems to try to understand locally free stuff on the pro-étale side in terms of locally free stuff in the analytic side. Seems to relate exactly these two things.
If I remember correctly, also Ben said in his lectures that pro-étale vector bundles were exactly like some special vector bundles defined by Fultons, right?
generalized representations. Yes.
Yes, like it's paper of p-adic systems.
Yes.
But
But he
that's
also
not-
shows that that it's very difficult to understand functions, and the hope is that after the lectures by Art, which will hopefully happen, and by Camargo, we will understand. But for me, this is something that
Yeah, they like in the Simpson correspondence, they certainly have some very fancy tools. I think Holdings just didn't have them, so you had to do it by hand somehow. But yeah, for now.
So I remember that Ben Course told us that files were great, but the random work is very dense, and
Right.
this is so only little by little last year the details started to expand. It's more transparent way, and this process is still forthcoming.
Oh yeah, I think there is a lot of movement.
Yes, there's a lot of movements, and it's not as simple as it's still not as simple as function, which makes it interesting.
I guess. Yeah.
Just ask a question. So is there a way of in this can you think of P1 as parameterizing formal groups in some way such that what you wrote? I mean, sorry, I'm just understand what you wrote.
I guess essentially, right? I mean, this parameterizes form a group together with the trivialization of the tape module. This is the torso that forgets that trivializations. But I guess you need to be a bit careful because the tape module is the ZP torso. So as GL to ZP, sorry. Right. And this map is a bit weird, I think. Like because you define this guy by trivializing the like just tape mode like the ZP vector space, right? So this gives you a GL to ZP torso of Earth. This living tape space of level 0. This guy parameterizes deformations of the former group. Yeah, and then going to here is a bit weird, I guess.
Is it somehow related to the Porch equation? So how suppose suppose we have let's say not a formal group, but suppose we start with a super simple
Yeah, I guess it's very
and
similar.
then we look at its deformations, and then given such a deformation, how do we extract it into P1 and also of which P1 is somehow.
Yes, I guess it's somehow looking at the quotient to the D algebra. This sample, you have the standard tape sequence, and then that gives you, right, to any guy in here, that gives you a canonical projection from two-dimensional space to some one-dimensional, or I guess you can also take the opposite, like a line in the two-dimensional.
So it's
That is
probably understandable in principle, but this is not your main point. This is just an example to keep in practice.
So just to clarify, this is the map that people call the gross. This is the
Yes.
gross
Yeah,
Hopkins
that's
period
that's
map.
correct, yeah.
Gross and Hopkins.
I mean, it works far more generally than here. But don't ask me about the details of the general thing. Anyway, so we have this local system, and this is truly a pro-étale local system. So this will not, we cannot construct this. Well, this will not be trivial étale locally, but of course it's trivial pro-étale locally, namely in this guy. And then David Hansen computed the cohomology of this. So, and what just need to find it. Ah, here. So if you look at the cohomology just on P1, this local system, then you end up with O0 I is not 1 or 2. And then if I is 1 or 2, you get a Banach-Colmez space, and I'll say a little bit about this in a second, of dimension 1, minus 2, minus 1, and you get a BC space dimension 1, 2, minus 2. Okay, and what is a Banach-Colmez space? Well, roughly, it's a topological QP vector space built out of finitely many copies of CP and QP. Okay, and the dimension, so this is the one here is kind of the number of CPs you use. And the second thing is the number of QPs you use. So you should think of like dimension 1, minus 2 means that you have a CP vector space and you mod out 2 copies of QP. And here, additionally, you have a CP vector space and you add 2 copies of QP. Okay, so and again, we see that something weird is happening, right? Because this thing is, as a QP vector space, this thing is infinite. It's a CP vector space. And if you're hoping for any sort of duality, you have to again mix CP duality for this version and QP duality for this version. So it's very similar to what happened here, except maybe it's a bit strange because like the space you're working over is a perfectly fine, very nice, proper space. I guess I could say even the nicest one there is, right? But even on that, as soon as you allow arbitrary local systems, something weird seems to happen.
Except in example 2, the spaces are infinite dimensions, right?
Yeah, here they even have dimensional CP vector spaces. Here they finite.
So is this why we want in the example to have this condensed mathematics to somehow.
Right. I guess this example you can explain without condensed.
Yes, I'm talking about example.
Here you need, yeah, I mean, to handle these infinite dimensional things, you certainly need condensed stuff.
Is there a general rule? Suppose I don't really understand anything that in the equation. Suppose in a more general situation, you have HI. Suppose that HI is a Banach-Colmez. So what happens? So for each I, suppose we are in a smooth proper situations. I hope that each I is a Banach-Colmez. Is it correct? Is it
Yes.
true? Yes, for any pro-étale local system.
Yeah.
Associated to this are 2 numbers.
Yes.
Now, if we replace the local system by its dual, so for me, since I don't know what a Banach-Colmez space is, for me, it's just 2 numbers, kind of betting, weird betting numbers. And what happens to these betting numbers when we replace the local system by the dual? Can I'm not sure that
The theory I want to present will answer that question.
What?
The theory I want to present will answer that question.
Yes, the first question, meta question, is whether my question has a definite answer. Because
Well, I
maybe I'm not, since I'm in an unfamiliar world, I don't know whether knowing just these 2 numbers or
Well, I mean,
the original local system determines these 2 numbers.
I would guess that the dual local system will end up giving you the dual Banach-Colmez spaces. Right? So I guess it will keep this 1, but it will like invert the number here.
Aha. So in other words, you are saying that the naive guess is correct.
Yes.
In the second, in your second line, you get 1, because there was 1 in the first line, and
1, 2, and
because
yes. But potentially
and
there's
that's kind of
also
a cool pattern recognition.
yes. Well, potentially you also have to be careful with the indices where they lie, but yeah, I guess the pieces you get will be relatively the same. Exactly. So how do we solve this? I guess you can maybe see this as a teaser to what Juan will talk about, I assume, when he's here, where he does a much more fancy version of this.
Who has a fancy book?
Juan Esteban Rodriguez Camargo.
Yes.
I was told he would come here in April or something, right? And like he is working with Achira and Johannes and Peter on doing a fancier version of what our present now. But I guess this will already, like, the general idea is very similar. At least if you care about only about Q. So what is the solution? Well, certainly there's no hope of getting a general duality or six-functor formalism statement if you just view these things as QP vector spaces. Because like, if I forget everything apart from the QP vector space, there's no way I can measure these things. So I have to replace, I have to view them as something else, and I guess I gave it away last time already. So we view this R gamma of X and QP as a sheaf on the Clausen curve over CP, I guess. I guess everything is over CP. Okay, and then I'll say something about what this looks like in this case in a second. But then, if you view, so basically what I'm telling you is I attach two C's and curve. I view the cohomology as an object contact curve. And then if I want to get the actual cohomology, then so then the actual cohomology is cohomology of this sheet. Oh, sorry, and this will be a quasicoherent sheet. This sheet. And so maybe I should quickly recall what the Clausen curve is before I can say how it works for the setting. So recall. Suppose well, I'm in the perfector setting again. And the Clausen curve is constructed as follows. The Clausen curve over X, maybe I should call this S. Clausen curve over S. I define as, well, I take the p-adic space associated to the ring of bit vectors over the tilt. Tilt. Then
Sorry, is that A plus spot?
Yeah, sorry, thanks. Or A flat plus, I never know which order to write these symbols. I guess it's the same. So I take the space, I remove the zero locus of P, and so I guess I, something in mind. Pi, so it's an element just an A plus. I remove the zero locus of P and like lift pi, and then I take the whole thing and I mod out the Frobenius action. Okay, so this is an p-adic space. And it lives over QP. So what does it look like? Yes, well, I hope the lid vectors and so on are familiar enough that I don't have to explain that. Okay. So I guess what you should roughly think of this way I think of this at least, some sort of function disk where the variable p is so it's power series. This guy's power series in p, so I can do this as some sort of disk, and then I remove boundary and the middle point, so it's some sort of function disk, and then I multiply the p-disk. So it's some sort of torus, I guess. So you're gluing function disk along, you're gluing analyte along the boundaries.
Yes, and when emphasize that it's over P, it's not over something bigger. So, for instance,
Yes.
when S is CP, when S is RC, then we still get something not over S.
And well, one thing about this is that the accumulators.
Sorry, this happen because of passing to the quotient with respect to phi.
Yes. The accumulators on degree 1 on that space. They correspond to functors of the tilde of S. So you can somehow, okay, up to Frobenius, I mean, without the Frobenius, that would be literally 2, and then with the Frobenius, then I guess that's acknowledged. So in other words, you can think of that thing. So in particular, if S is just a point, you can think of the Poincaré curve as a curve through all the untools. So in particular, let's see times a point all infinity on over C. Okay, and that point is literally the one, like on the split vector ring, you have the theta map going back to just, let's see, the point I have here is just the point given by that one. Okay. Now, how do I explain all this stuff here? Well, that in that picture of she's on the Poincaré curve, a QP vector space appearing in the cohomology that corresponds to copy of just the structure sheet on the Poincaré curve. Okay, and that matches with the observation that the cohomology of the structure shape on the Poincaré curve is just Q. So, okay, and a C vector space appearing in this one gamma. E corresponds to a copy of, well, you take the inclusion, the point, maybe then just to see it. Okay, so some of these C's that we see here, they're skyscrapers with one point. And the QPs we see there, like global, nice shapes. And now, if you now do a duality on the curve, then you see that the duality on the curve will separately take duality on the skyscraper stuff, on C, and duality on the QP stuff, and that is exactly what explains the dualities I have. Yes.
Sorry.
Yes.
So not every quasi-coherent shape on turn can be realized as Banach-Colmez space, right? You're saying that, so can we
Right,
take,
okay.
for example,
I never really know what exactly Banach-Colmez space is, but the definition I can from this.
okay, so like basically, can we say that like the category of Banach-Colmez spaces is equivalent to say that the category of quasi-coherent sheaves on the far content curve, which are generated by the structural sheaf and then the skyscraper and the
I guess. Well, I guess I would define it as just perfect sheaves on the far.
So I don't know what a Banach-Colmez space is. I should say that whenever I encounter Banach-Colmez spaces, I really have to think in terms of the far content.
Yes.
I don't know far content curve. I don't understand the far content curve either, but at least it's better to.
But from
there are known quantities, known motions to a smaller number. So your recommendation is work with the fractal curve and Banach-Colmez spaces, the automatic count. Now, is this I'm more familiar with the theory of dismissization of formal schemes rather than the story about the unleashed dismissals. Is there something parallel?
yes, I would say it's extremely similar, because. Well, I mean, what do you do in the prismatic step? Well, you start with a prismatic set, which parameterizes prisms together with categorizer.
Can you write the parallel statements if there exist parallel statements in the dismissization story?
Well,
Can you write?
Sure. I mean, so. I mean, I have not prepared this, so this should be not literally.
Yeah, I'm asking an illegal question.
So I guess you should see the black content curve over space X. Okay, I have not defined it over space X, only over the vector space. But you should see this, I guess, as an analog personalization. Oh,
Maybe what about passing to the quotient of parameters?
I mean,
okay.
This is a very
so anyway, a vector bundle on the function thing, something like an F crystal.
Yes.
Like a prismatic.
Yes. I got that.
I think it's probably closer to those F gauges, right?
I think.
And since I have asked somewhat illegal questions, so
I think prismatic is maybe. Well, I don't know. Yeah.
think about this in advance. So anyway, yes, possibly instead of observation, we have to. So anyway,
I mean, here also, if you have a prism, which I guess you can pair delta ring device. I guess these. Well, it's perfect. I guess these first, well, you should see as analogs. So, you have the 5.10 curve over perpetuate ring and characteristic P together with categorizer, which is an untold. And then from that perspective, I guess we can, like the definition of diamonds that I gave last Monday, where a rigid space I represent by mapping vector space characteristic P to choosing an until and mapping that thing. That is basically just saying that I represent a space by, for each kt divisor on some curve and map that to the space.
Yes.
And I guess that also gives some similarity of how you would.
Yes, and so suppose that I replace the function by the quotient of the mathematization divided by or maybe by the simplification of terms. But then you also in your story you also have local systems. Well, pro-étale local systems.
Oh, I guess we don't really.
Okay, if my question is illegal, then you don't have to.
Well, okay, I guess what you need to understand is that you take quasicoherent sheets, and I guess maybe you should then take a simple implication. I'm not that fluent with the language, sorry, but I guess do you have something like all shapes embedding into this?
Well, the problem is that the relation story, I don't understand where the Anschütz. Okay,
So maybe this thing is even recorded, but I'm just trying to. Okay, I'm not entirely sure, but I would expect something similar to do that. I'm sure there as well for the right version of whatever you have to put here.
Yes.
Okay. So somehow, I mean, I will say in a second, like in this setting here, I QP sheet, pro-étale QP sheets will embed into quasicoherent sheets. And I guess there should be some, well, at least that's expected. I mean, but I would expect that. I think something like this probably is true here in that setting if you choose the right step. And then I guess a pro-étale system will just be a quasicoherent sheet. Okay.
You just said pro-étale QP sheets are expected to embed in Q code or.
Yes, I mean not all pro-étale QP sheets, but in the same way as not all étale sheets have previous category. Or I mean, yeah, even that. Well, I'll write down a precise statement of what I expect. Okay. I guess so. I guess maybe this was hopefully enough motivation. I didn't say one thing. You have this weird shift of dualities happening here, right? And I think this comes from the fact that if you look at how that there's some shift in the duality. This guy. I think if you take a dual of this, you get this when the shift by one on the flat potential. Like duality on the flat potential.
But somehow this shift doesn't happen. If I understood you correctly, this shift doesn't happen in the proper case. At least in your example.
Here. That is indeed weird. Yes.
Okay.
Well, okay, but I guess maybe in this case things are a bit different anyway. I guess I would have to write down how exactly these things are represented. Sorry, maybe it's this.
Okay. The only thing is
It'll be a dual, right? It'll be something when there could be the L sub LT dual that would draw. Well,
Yes, right. Ah, right. You have a duality here as well, so maybe that mixes them up. Okay. I guess that's what's happening. So somehow, like here, so the shift comes from the fact that the dual. And this will be same, but then shifted. Okay. That's kind of what I don't know.
Yes.
Plus,
Minus.
yeah, right, next to the
So again, one question about numerology. So the fact that the Banach Colmez, you first said that the Banach Colmez space is built of two vector spaces. Then you told us that this pair of numbers is their dimension. But this is not the only partial truth. Because here you have a minus dimension cannot be.
Well, I mean, the minus means that I mod out, like I take a copy of CP and I mod out 2 copies of KP. Sense of, like,
So we really have something like this. So if you have a Banach Colmez space, then my understanding is that its dimension is a pair of integers. And this
the first one is positive.
What?
This
The first one is
this one is always
positive, but the other one
Yes.
can be.
I guess if you try to formalize the definition, in the definition, you will have more than just the topological vector space. There will be some more structural things in order to make these numbers work. But I don't. Yeah. I actually don't know from the top of my head how this thing is properly defined. Except that I would just view it as a sheet. That's the only
And since you can, since you were able to work with this point of view, this is in some sense also a recommendation for us.
Right. And that's not
whenever people talk about Banach Colmez, let's look for the try to interpret.
I guess it's similar to how you would try to understand F pages or whatever has sheets on that thing instead of whatever you could try to write on by hand. Okay. So let me now, so I already, okay, I guess I'll try to finish in maybe 10, 15 minutes. And I just want to say what you need to do now to implement this idea and how far we've gone with that. So let me say implementation. Right, and so what do we need to do? Well, the hardest thing to make this work is that you need to define what response actually you achieve.
So far there was just kind of key.
It was, yes. So I guess the hard part is to define this. Okay, and well, again, we will use solid mathematics, of course. So let me, so far I haven't really talked about non-discrete rings, so let me quickly mention how the solid set works in setting up non-discrete rings. Because of course the star contingent is an adic space, so the rings that appear in this definition, they all have a duality. But it's actually quite easy, so suppose that A is a condensed ring. I guess can be animated, but for today, let's just ignore that. And suppose we have some subring of A of star, so just A evaluated on star, so the underlying set of A. Then I define D solid A comma A plus to be all modules M in D of A such that M is solid as an A plus module.
So what is it that A flat is contained?
This is plus.
In plus.
This is just a name for the subring. You can also call it P.
And what is written after A and then something?
Some subring.
No, but A, is there a star?
A of star, right?
And so A is a functor, yes?
Yes, it's a condensed ring, so it's functor from profinite sets to rings.
Is A plus also a functor?
No, this is literally a ring in the most naive sense that you could find a ring. So it's just like this is a set, right? So I just take a subset. And well, this is a ring.
No, but just one is when you wrote star, does it mean a variable profinite set or what?
Yeah, sorry, yeah, that is the profinite set that has exactly 1 point. Sorry.
It's not a variable.
No.
It's
No, variables from here,
it's a
dashes.
single term.
Variable from either dash. But yeah, okay, sorry.
So is A plus inherent in any condensed structure?
No. But I think one has some fancy, well, maybe not the plus, but for the A-circ, you can define an A-circ in a condensed way.
Okay, so in the next line, solid as an A plus module.
Oh, okay, sorry, that was the question. No, yeah, so this is just in the sense of what I said last time. So this is literally just a discrete ring. And all I'm saying is that M lies in that thing if I forget the A module structure to an A plus module structure, then it's solid as a module of that. And you can see that this is actually equivalent to this category of modules over A in D solid of A plus. Okay, and in particular, this gives you now a definition of solid modules basically over any ring as long as you choose some submodule. So I can plug in topological rings. And okay, I also abbreviate. Abbreviate E solid A, just as E solid A, comma, and I take the full ring. Just and I should also remark that this category depends on this A plus only in a very soft way. So you can change this A plus around quite a lot without changing that thing. Like integral extensions in the A plus won't change anything, for example. Okay, and then there's here one remark, and this is maybe slightly weird or something that happens. Namely, suppose A is a p-complete ring. P-adic ring. So I just mean a condensed ring. Hey, oh, sorry, thank you. So that means A is p-adically complete. Plus A mod P is discrete. And I view it as a condensed ring. And then, sorry, I forgot to mention. So this category is generated by compact generators, and I'll just call them A, A plus solid S, so as before. And in this case, they are just, I take A, I times it over A plus. It'll be A plus solid I had before. I mean, it's easy to, from this description, and the fact that this guy in the middle, the D solid A plus is compactly generated, it's easy to see that also the modules are compactly generated, which is tensoring the modules. But the thing is that these solid generators over a p-complete ring need not be p-complete. Okay, and this turns out to be a big issue if you want to prove these VD-centered cells. So what we have to do in our work is, and I like the fact why they're not, I mean, they seem like they want to be, but the problem is that if A is large, then you define the solid generators by these colimits over all subrings, and these colimits they just support p-completeness. So we renormalize by saying I now define this category D solid hat A. which I just define as the int category of the category given by the p-adic completions for the compact objects in these solid. And okay, it's a bit weird that we had to do that. But like as long as A is small enough, so for example, if A comes from any, well, okay, you can also invert P, but like as long as you stay in rigid geometry over CP or over any field that has only finite transcendence degree over CP, this thing will be the same as the solid. So somehow the difference only happens if you allow really large spaces. But for example, one thing for which it does change something is if you take a totally disconnected space, because this thing as a ring is huge, like because it has all these infinitely many connected components. On these, it will change.
Is this contained in your thesis?
No, this is contained in this is part of joint work with Johannes Anschütz.
Is it already publicly available? So.
But well, the point I want to make is that this root normalization. Yes.
And your co-authors are who? Anschütz and Le Bras?
For this particular definition, only Anschütz.
But the question is, what? Suppose I want to understand the details. Where should I look?
Yeah, in this paper by me and Anschütz.
You and Anschütz.
Yeah, I think it's called VD-Cent for class coherent sheaves and perfector spaces. Right. So the point I want to make is that okay, it's a bit weird that we have to do that, but in practice, at least as long as you stay to rigid geometry over not so big fields, it actually doesn't make any difference. And then here's the theorem I have with Anschütz. And it says that, well, the same as before, there are unique hypercomplete species on the category of V-stacks on vector spaces. Sending such a V-stack to, well, now I have two, I claim there too. So the first one is the version with OX plus, and the second is the version with OX. And they uniquely determined, so such that nice, factory. And by nice, I mean exactly the same condition before. Same condition which also worked on P. We have solid at A OX plus stress D solid at A plus stress D solid at okay. Okay, maybe A comma A plus. Okay, and like the version for OX is a formal consequence of the version for OX plus. So it's really just one statement, but maybe the OX version is more important once I stated it as well. Okay, and so this is really something new. It does not just follow from the result I presented last time. The result I presented last time, by passing to the limit, you would get that you have to send for p-complete objects here. But if you only allow p-complete objects, you can't easily go to here. So somehow it is important to actually have the two-cent result for all modules here, so that we can invert. And well, from this, So not so hard corollary that it is a complete sheet. Going from V stack. So these are V stacks in characteristic P again. Oh. Send X to let me just boldly call this thing U of X to P, such that same if you have the vectors. Well, nice one. It's P of X to P is just the D solid hat of O. It's like quasicoherent solid hat modules on the one contained curve over X Z. Oh, sorry, it doesn't even need to be a pair.
So is this theorem proved using similar techniques as pure proof?
Yes, the main challenge was that in the ModP version, most of the proofs worked by, well, I reduced to some totally disconnected spaces, whatever, and then I worked over connected components of that. And because on ModP, that's totally fine. But if you don't go to ModP, but instead work p-adic way, you can't easily do that. So we had to replace the version of, like, yeah. I mean, yeah, it's somewhat similar to like étale sheets. You can understand we're looking at stocks. But if you look at incomplete sheets, then you cannot understand them by looking at stocks. So we had to come up with a different, like a replacement for stocks, essentially. Yeah. Right, and then for the expectation noise. There's a also contact formalism for this guy. Or maybe okay. So there's actually several you can do now. Maybe write them. And then more or less done.
Sorry, can I have one more question?
Yes.
Is this dx comma qp an honest dx comma qp, or is it just the same kind of shorthand notation?
That's shorthand notation.
Okay, so it's
This is far from actual sheaves of X.
So it's again tensoring basically everything by OX. Is it?
Yeah, it's similar to the ModP version.
And then is there like a value from that deep code thing to like the sort constructed?
Yeah, that's all part of will be part of the expectation. So we have a 4-600 formalism for this. This computes pro-étale cohomology. But there's other things you can do. You can also expect there to be a 4-600 formalism for X. So this gives you complete cohomology. Okay, and I guess you should see. But by definition, more or less. Yeah, it is more or less like this pro-étale cohomology for the structure sheet. So pretty much what you get out of this by definition. And it's quite different from pro-étale cohomology from the analytic cohomology structure sheet. Right? So completed cohomology behaves much more like étale stuff, which I guess makes sense because it's like in the same third as stuff. It is something that has been studied substantially in the context of Shimura varieties. Studying these completed cohomologies of Shimura varieties. I think Matt, for example, has worked a lot of that.
The definition is the same as Matt's.
Right. As far as I know, Matt only defines the cohomology. The cohomology will be the same. And this gives the full sheet theory for it, including like you get functoriality and whatever. And there's also one thing you can do. I guess I should mention that as well. You can take OX flat. So that now is a sheaf and characteristic P. And you can take phi invariance. This gives you another version of étale cohomology. Okay, so that is a bit confusing maybe. Because last time I presented to you the ultimate solution to a cohomology, now I told you there's another one. But yeah, it turns out there's two. So you can either take this, or you can take the one I gave you last time. They both come with advantages and disadvantages,
And they're different.
they are different. These categories are different. Yes. They both contain étale p-sheaves, like overconvergent étale sheaf p-sheaves as a full subcategory. So basically everything I said last time works also for this guy. One difference, one advantage this guy has is that it doesn't involve almost mathematics, which is nice. And this guy is literally compactly generated. The almost version is not. A disadvantage that this guy has is I think it does not satisfy excision. So the usual excision sequence I think fails in this setting. So yeah, I don't know. Also, the other version I guess embeds into V sheaves of the p-vector spaces. This one I guess does not. But then again, this one seems closer to Langlands. Like if you wanna, I think with this you can more or less formally construct the image stack. Like by formal recipe that apply to this formalism. Yeah, whatever. I don't know. There seem to be these two choices, and I don't really know which one I like more. But like in practice, I guess it doesn't matter too much as long as you have a 600 formalism. And also, there is an embedding. So that would be a version of the Riemann-Hilbert functor, the Riemann-Hilbert correspondence. So maybe I don't know. I should call it Riemann-Hilbert in this case, but. So there should be embedding of nuclear p sheaves over convergent into this guy. And this here, this d-nuke is the subcategory of all pro-étale sheaves. Such that F is a colimit of Banach sheaves. And the Banach sheaf is pretty much what you expect it to be. Like it's it's a p-complete sheaf, which is mod p-étale, and then you insert p. Okay. So I mean, this d-nuke is the analog of d-étale. I mean, it doesn't make sense to speak of étale QP sheaves. So I guess you speak of something like int-Banach sheaves. So that would, I guess, be the closest to étale QP sheaf. So this contains again all local systems, for example, and it embeds into you. Right, and I guess that's all I wanted to say. And I guess if you go to one talks, he'll probably present you a fancier version of like this analytic crystallization that you take.
Who will present?
One Esteban Rodriguez.
One Esteban.
So basically, the idea is to replace these micro curves by some fancier version. And then, like with this version, you can see pro-étale cohomology and completed cohomology. Like you should see this OX as just sitting at this point infinity, right? And with a fancier version, you can see all sorts of p-adic cohomology theories. Okay. Yeah, thanks a lot.
How much of this expectation part has been done?
So constructing the six-functor formalism, in these two cases, I think we more or less have, and in this we expect to be just formal. So I guess you could say the six-functor formalism is more or less done. I mean, not written, but we've worked out all the details, I think. And then this I haven't thought too much about yet, but I don't think it should be very hard, actually. I guess well, one thing that this solid hat version really facilitates is that you can reduce a lot of things mod p. And that's really why we want to do. At the end, also this theorem, at the end, I guess more or less works by reducing mod p. And I guess something similar you can do here as well. Yeah, but this I haven't thought about yet. So I can't say for sure. But once you have that, of course, you also get results like this Fontaine curve cohomology has been considered before, and I think there were open questions like just to push forward along a proper smooth map to preserve perfect objects in the Fontaine curve. And these kind of things we can prove now. Together with we can prove Poincaré for QP cohomology in that sense. Kernel's formula for Poincaré in that sense, and so on. All these things are formal once you have the 6 features. Maybe I should say one thing. If you don't like the head, what you can also do instead, of course, is instead of working with lead stacks, you can work with a much weaker topology. Essentially, I guess that is probably what one will choose to do. Essentially, what you can do is you can just work with the best, like strongest topology for which this thing has descent or something like this, and you can always do that, right? Then it's not so clear how it relates to all the theory in Clausen Scholze, but at least you get this descent. I mean, basically, you get the descent for free. You get the 6 functor formalism for free, and then you have to work a little bit to see for which kind of spaces you can actually apply the stuff. But for rigid spaces, you can basically just wiggle your way through, and so for rigid spaces, you can get away without that. So yeah, I guess maybe that's also a matter of taste.
Actually, just one question I have about the hat construction. So mod p, this is we have to almost basically this is a category explained in the previous lectures. And that would imply that like the p complete category satisfies the same free descent. I was just wondering if there's some sort of, is there some general way of like starting with a category that's p complete and decompleting it? That's
What do you mean?
sorry, this is a big question, but so I guess for example, when Sasha Akama was here, was explaining how a version of this theory of nuclear objects.
You can take as a limit and
Yeah.
category dualizable categories.
Yes.
Yeah, I guess you could try to do that with these categories mod p to the n. But I haven't figured. I mean, I haven't tried to, but I don't really know what you will get. I mean, even just for ZP, you get something that's bigger than DOZP. Like if you take the limit of DOZ mod p to the n, what do you get? It's a bit
There's
bigger.
some version of nuclear.
Yeah, but it's right, but it's not exactly the same.
Yeah, something like
Yeah, I was always a bit confused by that. Yeah, I don't know what you will get.
And also, is the issue that that prevents these things from being p complete in general? Is the issue of a plus? Is the issue entirely about a plus?
Yes.
Okay.
Yeah, so as long as A plus is small enough, that's fine. It doesn't change. And also, even if A plus is not like this, D head solid, like inside of this, you can define the nuclear category, right? And it does not depend on that. So, and I guess the nuclear category is maybe the one you're most interested in at the end anyway. So nuclear sheaves, there's no difference. So you get, well, in particular, out of this, you get descent from nuclear sheaves, not protected. Yeah. So also perfect objects, vector bundles, all of this lies inside of part of this, which is independent of the head. Only when you allow like very solid things, you really need that. I'm pretty sure the descent does not work without, at least I tried for a long time.
Other questions? Oh, I was just gonna ask also, is there's an analog of homological smoothness in the setting? Is it possible to say what the like the analog of the tape twist is here?
Yes, okay, that's another expectation. So if we can make it work, okay, well, I guess one thing no one asked me about, but which is maybe a canonical question. Is there also a version for this? Okay, and there's two things you can do. You can either take a different version of the product potential where you don't remove the p here, and take that as the definition. So that would be somehow the geometric version of the coefficients. Maybe that's the better one. I don't know. But what you can also do is just naively take this curve and take x plus modules and map it. And I guess the same kind of arguments will give you 600 formalism for this as well. If you can make that work, then it allows you to connect the theory for QP to the theory for x plus mod p that I sketched last time. And if that is true, then it's completely formal that a map is smooth in this sense, if and only if it's smooth in the mod p sense, and the dualizing complex is also matched. So you get, I guess, a similar Tate list. Yeah, maybe that's slightly remarkable that smoothness mod p implies smoothness for QP, but yeah, it turns out if you think about this in terms of this abstract 600 step, like being smooth is a condition that only depends on very few data. And it turns out that this data in this case is p-adically complete, so you can reduce it.
The other question. That is kind of speaker.